So our speaker now is Eugene Demler. We're very, very happy that you came.
Thank you.
And, OK, please.
Thanks, Avi. I want to join other speakers in thanking the organizers for inviting me and congratulate on the center. And say, from my personal experience, being part of the center can be dramatic, can have dramatic effects. Like, say, I was trained in sort of conventional commencement traditions and as a dogma that say you either work on high TC or you do stamp collecting. And then after I sort of started interacting with my colleagues at Harvard and MIT, after joining at CUA, I really changed my perspective on things. Now, for example, I publish as many papers in PRA as in PRB. I think that also, so I want to wish you guys also kind of quite exciting journey, and I'm sure being part of the center can change you as much as along the way as you try to build it. So, OK, I'll tell you today about the work which we have been doing recently, and people who did most of the work for this project are really Saranga Balakrishnan, who recently started his own group at CUNY, and Tao Shi, who is a postdoc at the Max Planck Institute. But it actually, a lot of this work traces back to my interactions with Emanuele, who convinced me that, say, looking at, say, atoms in a cavity and decay model that he told us about is also an interesting many-body problem. And you'll see, I hope I'll try to give another aspect of this as we go along. So in this audience, I don't have to convince you that when we talk about many-body systems, like the finding ground states or looking at dynamics, this is really hard. That in most interesting cases, we cannot do it exactly because Hilbert space grows so fast. And then especially in dynamics, semi-classical approximations are quite poor. We don't have well-defined quasi-particles. Retardation effects are important. Hydrodynamics is very suspicious because coherence is important. Hydrodynamics usually does not take care of that. So the approach that I'll try to advocate in this talk is to use variational approach, which is means to take classes of wave functions. It's not exact solution. We sort of look in some restricted class of wave functions, but we'll try to make them rich enough and sophisticated enough to capture essential physics, yet simple enough that they're computationally tractable. And of course, you can the most famous examples of variational approach would be, say, Gross-Pitaevsky equation, when we assume that, say, for bosonic particles, all the atoms are in the condensate, and then we just write self-consistent equation on this condensate wave function. Or for fermions, we can have a self-consistent Slater determinant solution, which is gives us time-dependent Kortchev-Fock equation, and that, for example, can be used to calculate really non-trivial phenomena, such as Higgs-like mode in Fermi superfluids. But this is relatively simple examples, and I'll try to argue that we can build upon this and look at even richer systems with kind of less obvious outcomes. OK, so this is an outline of my talk, since just spending too much time on the formalism would be rather tedious. So I'll give you a general idea. So it will be kind of a geometrical approach to thinking about dynamics, like for general classes of variational states. And then I'll focus on specific examples. And since a large part of the audience has optics background, I'll spend most of the time talking about like a two-cavity system. And one of, so we already heard from Emanuele that if you take a cavity, we can have self-organization transition, which looks like a decay transition. But recently, Tilman Esslinger's group realized a two-cavity system. And then the question we can ask is, well, what's the new physics that we can get? And I'll show you that we can get a very exotic phase in which we don't have superradiance in individual cavities, but we get a phase in which cavities lock with each other. So that's the so-called hidden order phase. And then I'll give you, so this, in this case, will actually restrict it will be sufficient to use fairly simple classes of, simple class of wave function Gaussian states. Then when we talk about something more sophisticated, such as a Condor problem, we'll have to use more kind of sophisticated wave functions which go beyond the Gaussian states. And I'll show you that we can use them to actually to study dynamics. And in fact, we were able to solve problem which, as far as I know, is not could not be solved by best existing numerical tools such as NRG. And then, okay, I'll just give you an overview of other approaches, of other systems which I think can be solved using this variational technique. Okay, one thing that I want to emphasize is that when I talk about dynamics, I sort of understand it quite broadly. This also includes looking for the ground state. From my point of view, this is just dynamics in imaginary time. So let me remind you how the argument goes. So let's say if we want to find a ground state, then what we can do, assuming that, let's say, we could solve the problem exactly, we could start with an arbitrary initial state. As long as it has non-zero overlap with the ground state, then we can simply evolve it in imaginary time. This is like the usual kind of Schrödinger evolution, but you can see the time is imaginary. And then the ground state decays the slowest, so you can see that as tau goes to infinity, what we'll get at the end of this evolution will be the ground state. And this can also be formulated, like this dynamics can be formulated as a differential equation on the wave function. And now, basically, what we want to do when we think of variational wave functions is to say, well, let's say we have some class of wave function. And, okay, it can be quite general at this point. And it has certain variational parameters. Then what I want to do, I want to project this equation, basically this evolution in imaginary time, just onto my kind of manifold of variational wave functions. Let's say, schematically think about this. Let's say this is a manifold of wave function, which are parameterized by different values of parameters. So how do I do this projection? Well, so what I do is that if I start with some initial, with some point, right? Let's say I have this variational state, instantaneous variational state. Then I can define a tangential plane, right? I simply differentiate my states with respect to my kind of coordinates parameters in my variational state. This gives me basis vectors. Okay, I define a Gram matrix for these vectors. And then, okay, so my time evolution, right? So how it should evolve, my wave function is given by, again, just this Hamiltonian minus expectation value of Hamiltonian or the energy acting on the wave function. So think about it as this wave vector. So generally, right, if I, when I think about this operator applied on the wave function, of course, it takes me outside away from the tangential plane. Sorry. From this tangential plane, and all what I have to do is just project this wave vector, sorry, this state, right, which I think of like onto the tangential plane, and it's very easy to check that this projection gives us exactly equation on the evolution of these variational parameters in time. And what one can show is that doing this approach actually guarantees that as we move on this manifold of variational states, we're constantly lowering the energy. So at the end of the evolution, when we find a steady state, we're actually finding a state with the lowest possible energy in our manifold. And then we can apply the same approach to dynamics in real time. Again, dynamics in real time is basically we have to apply the Hamiltonian directly. And again, generally, this gives us a state which is sort of taking us away from the variational manifold, but we just do the projection using the same into the tangential plane using the same approach. And again, this is a rather clever method because, say, it conserves energy. In fact, you can show that if you have any operator that's an integral of motion, it will be exactly conserved using this transformation. Sorry, it's pretty hard. So is there, should I just use another microphone? Thanks. Okay, right, and so just to remind you that there are some very simple examples, and this is a Gaussian states. So in the case of bosons, these Gaussian states are constructed the following way. So it's basic. We start with a vacuum of bosons. And then we apply operators which are linear in creation and annihilation operators and quadratic. Okay, we'll talk about this more. But the idea is that by specifying this coefficient in front of the linear term, right, we're specifying expectation values of bosonic operators, and then we specify correlation functions. And then for fermions, we can do again the same thing, except that linear terms are not allowed, right? So we can only have quadratic terms. Oh, sorry, that's supposed to be a vacuum acting on the vacuum, and this gives us a correlation function of the fermions. But the biggest problem of these Gaussian states, when those underlie all of our mean field kind of physics, and I'll give you more examples as we go along, is that they are sufficiently simple that they basically obey Wick's theorem. So all high-order correlation functions, for example, can be reduced to just to first and second order correlation functions. Or when we think about systems which have both bosons and fermions, the wave function just has to factorize between bosons and fermions. So it doesn't allow us to describe sufficiently rich classes of wave functions. And therefore, we have to come up with kind of more interesting wave functions. And I'll show you that this can be done by actually extending some of the earlier approaches, sort of this canonical transformation. But what's different between canonical transformation used before and what we'll do now is that usually you sort of do canonical transformation with fixed parameters. Whereas in our case, you can keep these parameters as your variational parameters, and you just do this sort of geometrical variational approach and minimize with respect to parameters of the transformation. Okay, so this was kind of a general overview of the technique, but let me now give you some specific examples. Yes? You can, let's say Gaussian transformation can be thought of as doing Bogoliubov transformation. Yeah, you can think about it this way, yes. But this is somehow, let's say, this transformation is actually more subtle. What it does, it really entangles, let's say, it can entangle phonons and electrons. So that I'm not sure how to interpret in this. Well, okay, you can think of, like, often you'll see that it can be a change of basis, say, from the original particle to a quasi-particle, to a polaron. Yeah. Okay, so let me start with my first example, and this is a two-mode cavity example in superradiance. And in this case, you'll see that we'll use just simple Gaussian approach, but it will give us a very non-trivial result. Okay, so Emmanuel already introduced the idea of the decay model, which is basically we have, say, atoms, and we have a single mode cavity, and then we can basically sort of atoms can be excited by emitting or absorbing photons into the cavity. And one of the interesting realizations of the decay model, most relevant to my discussion, was a realization first done by Vladan Vuletic and like in the thermal gas, but let me talk about the quantum version done by Tillman-Esslinger. So think about the cavity, and then we have a BC in the center, right? And then there is a pump beam. So I can, if I think about my condensate, right, I have atoms at momentum equal to 0. Then what can happen is that by absorbing a photon from a pump beam and then emitting into a cavity, right, my atoms can scatter into 4 of these states at finite momentum. Right. And therefore, now I can think about a two-level system where atoms basically can be in the original state k equal to 0, or they can scatter into a superposition of these 4 states at finite momentum. And you can show that this problem maps exactly into decay type model, and this kind of decay transition just corresponds to self-organization where atoms make checkerboard type pattern. And this checkerboard pattern, of course, has you can have 2 structures, and this structure corresponds to the phase of the condensate at finite momentum having, let's say, plus or minus sign with respect to the original condensate. Okay, let me, again, for people who are not familiar with this, let me try to explain the origin of this transition in a slightly different language. Let's think about the system this way again. So this is my condensate, this is a mirror, this is our pump beam, right? And then we have a standing wave which corresponds to a cavity beam. So now, okay, we treat the original condensate atoms, okay, as a C number.
if I put atoms into a finite momentum state, right, these states, then it will cost me some finite kinetic energy. This is recoil energy. If I have photons in a cavity, okay, then it costs me also some energy. That's detuning energy of the cavity relative to the pump field. And then, as we said, I can have a process in which, say, atoms maybe first absorb a photon from the pump, emit into a cavity, or maybe first absorb from a cavity and emit into the pump. And that's the kind of coupling that we get, that we have creation and annihilation operators for the cavity and creation and annihilation for a term for atoms in finite momentum states. And of course, we don't write annihilation operators for the condensate because we treat it's a condensate, so we treat it as a C number. So you see that this is kind of like a simple quadratic Hamiltonian. And now you can think about it this way. Typically, experiments are done in such a way that recoil energy of the photons, of the atoms, like this term, right, is much smaller than detuning. Now this is like mixing between two harmonic oscillators, and then we start getting level of repulsion, and at some point the lower energy state just touches zero, and that's the superradiant transition, right? So the original state becomes unstable, so we start getting macroscopic occupation of photons and atoms at finite momentum. And okay, just remark that typically in experiments, what we're interested in is just this low energy polariton, which is a superposition now of atomic excitation and photon, right, which you just find from by diagonalizing this Hamiltonian. And it's mostly atoms, but it has some admixture of photons. Okay, but now let's talk about the problem which I stated originally, which is let's take two cavities, right? So. And let's assume that basically cavities are at some angle with respect to each other. And we can give roughly the same arguments. The main difference is that now if we start with atoms at momentum zero, right, they can absorb, say, a photon from the pump and emit into the cavity, and it can be cavity 1, right, in this direction, or it can be cavity 2 in this direction. So again, we have terms which describe recoil energy, finite kinetic energy of atoms with this finite momentum. We have finite detuning of the cavities, and we have processes in which cavity photons are created and annihilated, and then we create or annihilate atoms in this finite momentum states. Well, okay, one difference is that now we have kind of states which have different momenta. They're not exactly degenerate, so we cannot just talk about take a superposition of all of the states. But that's not so important. Let's see if I just think about what's happening to cavity 1, right? And cavity 1 really just mixes this momentum states. Now I need to introduce two recoil energy kind of the atoms which have a smaller magnitude of momentum and a larger magnitude of momentum, two recoil energies. This is my detuning of the first cavity, and again, when I start mixing them, I see one of the branches, kind of the lowest branch, which goes soft. Okay, so far so good. So from like at the level of quadratic model, you would say, okay, I just have two superradiant transitions, nothing particularly exciting. But the interesting question arises: well, what if we go beyond this quadratic order? How does the system decide whether, let's say, it wants to order to have superradiants in just one cavity or the other cavity or two of them simultaneously, whether they sort of stand in the way of each other or help each other. And if you if you remember your statistical physics class, this is very common in kind of many condensed matter systems where you have different types of order. And typically this is described using Landau theory. Imagine that you have two order parameters. So we have quadratic terms which tell us whether, let's say, when this coefficient become negative, then phi 1, like the first, let's say, phi 1, the first order parameter wants to develop expectation value. And then we have quartic terms. And so I assume that these are both Ising fields, right? So they can be plus or minus. And then we can write three types of kind of quartic terms, which is self-interaction for the first field, self-interaction for the second field, or interaction between the two. And then there are basically just two cases, either kind of interaction between the when the interaction between, sorry, did I? Maybe, okay, if the interaction between the two fields, I think I think it should be reversed. Between the two fields is not strong enough, then we can get a phase in which two orders can coexist simultaneously, or if the repulsion between the orders, sorry, this inequality signs should be opposite, repulsion between the kind of mutual repulsion is too strong, then we get a first order phase transition, that the system either has one order parameter and not the second, or the second and not the first one. And then there is a special point when, let's say, this U12 squared is equal to U11, U22. It's a point of higher symmetry, which actually has been realized in experiments at ETH. But, okay, no, but let's say if we want to just develop this type of theory, then the steps that we would do would be to say, okay, well, let's take our fields. In fact, we know that we need out of, let's say, all of these states, like we have photons, we have atoms at finite momentum, I just need the lowest energy polaritons. So let me just take quadratic theory to identify my lowest energy polaritons for the first transition, kind of the first cavity, superradiance, and the second cavity, superradiance. So kind of then we can diagonalize the quadratic part, just keeping track of those low energy polaritons, and then start calculating the higher order terms. And so where do the higher order terms come from? Well, just think about the original Hamiltonian, right? So I assume, so this n is the number of atoms in the condensated k equal to 0, which we just set to be the original total number of atoms. But in reality, of course, once we start populating atoms at finite momentum, then we will have less atoms at momentum equal to 0, and therefore, so this n, instead of n, we will have to take the original number of atoms minus the number of atoms at finite momentum, and this will give us quartic terms. Okay, so this would decide what, like according to Landau theory, which type of transition we have. But actually, what I want to argue is that this is not the full story. You can get a much more interesting phase. And so what's the kind of simple argument for where this phase can come from? So let me think about kind of the following processes. Previously, when writing the say quadratic terms, I always relied on having one of the pumped photons. But now imagine that I have a process in which I'm using two cavity photons, like a photon from the first cavity and the second cavity. And this gives me bosons at finite momentum, right? So, well, it's a cubic term, right? You can say, okay, it's cubic terms. Say, if I think about soft modes, I wouldn't even include cubic terms, right? I am only interested in quadratic terms. Well, that's true, but let's say under certain circumstances, in particular, if the angle between the cavities is small, the state of that finite momentum, right? The recoil energy of atoms, which we get by scattering by two photons of both cavities, can have a low kinetic energy, right? And so what this means is that if we write some kind of effective theory, right now, again, I have these two low energy polaritons for cavity 1, cavity 2, and I have my bosons at small kinetic energy. So this, remember, that to begin with, energy of polaritons is mostly recoil energy of atoms, right? So it's recoil energy, kinetic energy of atoms at this momentum states. But now this kind of new field chi starts with a smaller kinetic energy. And even though it doesn't come in quadratically, it comes in the cubic order. But if we think about kind of level of repulsion, because it starts at a very small, at a smaller value of kinetic energy, because of this kind of sort of virtually converting the field chi, right? So we have this coupling which allows to convert chi into two polaritons and back. We also get the energy of the sky mode going down to 0, and therefore it can actually soften before we get transition before we have softening of individual polaritonic states. And okay, and so that's then the problems that we want to solve, and basically what we do, we just have to minimize this our Hamiltonian, right, with respect to Gaussian states. And let me just take you through the phase diagram. So these coupling fields, this is basically controls how far we are from superradiance for, let's say, cavity 1 and cavity 2, right? So when we're, let's say this lambda 1 is negative, right? So it's the first cavity wants to go superradiant, but lambda 2 is large. Okay, so we get a transition into a phase where the first cavity is superradiant. Like this blue corner, both lambdas are large, so we don't have superradiance in any cavity. Now, this green corner is actually when the second cavity wants to be superradiant and the first one doesn't. So we get superradiance only in the second cavity. Then when both lambdas are negative, means both cavities want to be superradiant, we have kind of simultaneous superradiance in both cavities. But something quite interesting happens in between. It's a phase in which we do not have expectation value. We don't have coherence inside cavity 1, and either cavity 1 or cavity 2. But we have expectation value of the product of the photons. So what this means is that our cavities became coherent, right? Photons are correlated in the phase. It also means that we get macroscopic occupation of atoms at this momentum chi, right? But so it's kind of exotic phase which is beyond the simple mean field. So if we see, the usual mean field does not consider the Gaussian part of the wave function. It only assumes that we have condensates of bosons without including the kind of the quadratic part in the wave function. Okay, so let me just say a few words. So when we do calculations, how exactly do we do them? It's technical. I just want to give you a general idea, right? So as we said, it's the general Gaussian state is, you can really think about it as just a generalization of what you learned in your basic BC class. Remember, you start by saying, oh, I have a condensated K equal to 0, which has most of my atoms, but I also have quantum depletion, right, which is this quadratic part in the wave function. So this Gaussian state is precisely this form. So we have a coherent part, which is linear in creation and annihilation operators, and then we have a Gaussian part. And then what you can do, as we said, or you can just we want to do some kind of flow in this variational manifold, and you can formulate it in terms of equations of motion for the expectation value of bosonic operators and correlation functions. So if we take, the usual Gross-Pitayevsky equation, where we assume that we only have coherent state, then this correlation matrix is just 1, and you recover, that's the usual Gross-Pitayevsky equation. We get time evolution of the expectation value of like this macroscopically occupied wave function. But if we add Gaussian state, that's what we would usually describe as Bogolyubov equations. So we also get this kind of evolution of the Bogolyubov of the quantum depletion part, and then we just evolve it until we get the lowest energy state. Okay, so this was a simple example. As I said, well, we could get away with a Gaussian state, although the answer was rather non-trivial. Now let me take something non-trivial where we have to go beyond Gaussian states. And again, I want to start with a model which looks familiar to people with optics background. Think about a two-level system coupled to, say, a one-dimensional waveguide, right? So I have an atom, which I write as a spin and a half, and then I have some kind of like photons which have a dispersion, right? And then I have coupling between the spin of the atom and photons. Well, in fact, the same problem is quite common in solid state physics, where usually it's kind of formulated in a rotated basis. Instead of using sigma z, we would use sigma x and think about like any two-level system, say a spin. And then we have a magnetic field which can flip the spin between two states, so you can have a particle which can tunnel between the two minima. And then we have some degrees of freedom, which can be phonons. But this phonons coupled to the spin. So let's say for cold atoms, this can be BC, which couples to internal state of the atom, or again, in solid state. If we have an impurity which tunnels between two states, phonons can adjust themselves to a given position of the impurity. So you see, it's kind of the same Hamiltonian, just rotated basis for the spin. So let me just use this description. What I don't have time to explain, but there is actually another famous problem in condensed matter, which is related, closely related to this problem, and that's the so-called Condor problem. So think about one impurity spin interacting with fermions, right? So you can have, in this case, we can, right? So we can have, this is a spin flip process for the impurity, right, which couples to this spin flip process of electrons at the position of the impurity. And then we have also Jz with the z component of the spin of the impurity couples to a z component of the electrons. And the phase diagram of this Condor model is rather non-trivial. So usually we just think about it, oh, it has two regimes, whether J is ferromagnetic or antiferromagnetic. So if it's ferromagnetic, then it's irrelevant, and if it's antiferromagnetic, it's relevant. But that actually argument only works if we have perfect SU2 symmetry. This is when Jz is equal to J prop, so it's on this line. Actually, even on the ferromagnetic side, as soon as we break the SU2 symmetry, say this is our G flow, which describes ground state, which describes equilibrium properties, is rather non-trivial, because first J tends to decrease because the system remembers that it's ferromagnetic, but then at some point it will actually realize that while it's above the separatrix line and Jz, so Jz is the same as J, parallel in this notation, right, will actually change sign and will start flowing to positive values, right? So as in the course of RG, actually even the nature of the interaction between the impurity spin and fermions can change. Okay, I will not tell you how to show relation of this problem between exact relation between Condor and the spin boson. Let me just point out that this transition between this kind of where this J's flow to 0 and J relevant is equivalent to localization transition of this two-level system. Either, let's say we have two-level system, either particle gets stuck in one of the state or it continues tunneling. Okay, so now I want to solve this problem either for the ground state or even describe dynamics as a variational wave function. And the Gaussian ansatz would not work because then what I would, within the Gaussian ansatz, I would have to factorize my wave function between spins and the bosons. And that's not very good. But what we can do is, as I said, well, try to go a step beyond the Gaussian ansatz and do, in this case, it's so-called partial Polarant transformation, which was originally introduced by Silby and Harris. And roughly, the idea is that we entangle degrees of freedom between the spin and the phonon bath, right? Again, this is something which is linear in phonon creation annihilation operator. So you can think about this operation as doing displacement on the bath degrees of freedom in a way which depends on the spin configuration. And now what, so again, the way Silby and Harris have done, they would just try to optimize, like with respect to the ground state, this parameters lambda, and also when they looked at the state of the boson, they would not consider a generic Gaussian state, they would only consider a coherent state. Now we do a kind of a step further, and we sort of do flow either in imaginary time or in real time while keeping all of these parameters of this partial Polarant transformation as our variational parameters, and also treating this Gaussian state, which we take for the bath, as a free parameter. Okay, let me just show you results that we get from this sort of by projecting to the Condor model, because the reason we came across this problem has to do with like certain realization of the Condor problem in cold atoms, but okay, unfortunately I don't have time to explain it, but what we were really interested in is if you start with an isotropic Condor problem, let's say anywhere on this phase diagram, including sort of away from the symmetric SU2 symmetric point, how will the quench dynamic look like? So let me just, so what we showed is that with this kind of variational ansatz, we can reconstruct, by doing flows in imaginary time, we get precisely the same phase diagram as for the ground state. But what I find more exciting is that we get real-time dynamics, and it's rather non-trivial. So let me just show you some of the examples. So if we start with the antiferromagnetic case, right, J parallel is positive. So, okay, and I forgot to specify, again, the specific problems that we're looking at is start with the Fermi C, which doesn't see the impurity, right? Again, because cold atoms usually explore quench dynamics. It's more natural experiments. And then you suddenly add an impurity spin. And in this case, we start with an impurity which has spin up, right? So it was not there, and then it shows up. And so we're basically looking at a process in which Condor cloud is being formed. And this plot shows you spin configuration of fermions around an impurity as a function of time. So this is distance, this is time. So what you can see is that, okay, if we're on the antiferromagnetic side, so impurity is spin up, therefore we expect to start, and this is again what we're, of course, like then this spin, the impurity spin starts flipping, but what we're doing, we're saying, okay, if you take part of the wave function when the impurity is spin up, how does the kind of spin of the fermions of electrons next to it looks like? In this case, since we're projecting on a state in which impurity has spin up, we have antiferromagnetic coupling, the electrons should have spin down. And indeed, what we see is that this condor is formed over some time. And then, of course, what it means is because we started with spin up, then there is like, so we sort of have a spin down component of electrons, which is now localized near the impurity spin, which means that spin up is being emitted away from the impurity. We see this kind of emitted cone. Or if we start, let's say now we start on the ferromagnetic side. So in this case, when impurity has spin up, right, so the surrounding fermions also want to have spin up, and that's why now it's red. And the kind of the spin down wave packet is sent to infinity. But let's start in this phase. This is the most non-trivial phase that actually, to begin with, we have ferromagnetic coupling, but it's anisotropic, right? So in this case, Jz is less than J perpendicular, right? So you know that this flow should be such that J's first become kind of less relevant, and then they become more relevant with a change of sign. So originally, we just asked people who are experts in RG, like Georges Arendt and Jan van Delft, okay, can you guys help us solve this numerically? They said, oh, no, you know, this so many finite time crossovers, you know, you want zero temperature, no way, we cannot do this. That's why we, okay, had to try this variational approach, and it actually gives you very interesting results. So at short time, what you basically see is, well, to begin with, Jz is ferromagnetic, and that's why for spin up, we see that the surrounding electrons, they also get spin up, and spin down component gets emitted. But then, after some time, you know, it's real-time dynamics, right? It's not equilibrium, so it's kind of unfair to compare this real-time dynamics to the ground state, but somehow it seems to mimic it. At finite time, the system actually discovers that, no, actually now I'm looking at long time, this is sufficiently low energy degrees of freedom, and therefore I should switch to antiferromagnetic coupling, and therefore my kind of screening cloud switches from being spin up to being spin down with another kind of spins of, in this case, it's now spin up being emitted to infinity. So it's kind of intriguing that we get this complicated dynamics from these variational wave functions. Okay, so how much time do I have? 4 minutes. Okay, so now let me just give you an idea of other types of problems where I think this would be a promising approach. So let's say we can talk about polarons. Let's say one impurity atom, say one fermion interacting with a bath of phonons, right? And this specific coupling that can be like this electron can couple to the on-site. Phonons can couple to electron on-site, or they can couple to the hopping element for the electron. So the way to solve this problem is to do Lie-Low-Pines transformation, which again you can think about. It's kind of like similar to the Silby transformation which we saw before. It's a shift of phonon degrees of freedom, which depends on the position of the electrons. And then effectively what this uses is the fact that total momentum of the system is conserved, and that's why we can effectively integrate out impurity because we know, if we know, say, the state of phonons, we know the total momentum of the phonons, then it automatically tells us the state of the electron. Again, I'll just give you the highlights. So it's known that if we take the coupling to photons, which depends of the SSH type, when phonons couple to kinetic energy of electron, there is a phase transition. When we think about the dispersion of the electron, at strong enough coupling, the minimum of the dispersion is no longer at k equal to 0, but at finite k. So previously, this has been studied using Monte Carlo. We see this from the variational wave function, but from Monte Carlo, say you cannot calculate spectral function except by doing this kind of analytic continuation from imaginary time, which are very unreliable. Again, this variational wave function allows us to calculate spectral functions. Or we can, so I talked about the case of just one electron and phonons. We can have many electrons, right? So we can have finite density of electrons, right? So there is a hopping of electrons. Oh, there it is. And then they are coupled to phonons. And again, we can do this so-called Lang-Firsov transformation. Again, like typically, like in textbooks, they would take just one parameter, like this lambda would be just one number, which you fix once and forever to do. But in this case, we can keep it as variational parameters, which we minimize along the way. And this can be used to study not just the ground state, but also, say, response to external electromagnetic field. We can study topological states, such as fractional Chern insulators, doing, again, this kind of unitary transformation, which looks like flux attachment. So I'll be happy to talk offline. So this takes me to the end of my talk. I try to give you a general idea that we can sort of find something that hopefully, well, at least in some cases, can replace much more tedious diagrammatic calculations. And this is analysis based on variational wave functions. I give you a few examples where we have already demonstrated that this variational wave function gives very interesting answers. And I think many other examples can be worked out. Thank you.